Hey everybody, we're here for Unit 13 about weather systems and storms. I should rename the title of this actually to hurricanes. So that's kind of what we talk about or focus on mostly in this. I have my furry intern here with me today. This is Vino. He is not shy for the camera because he doesn't really realize he's on it. I promise if you come over, you'd probably never ever see him again because he's not the most, not that he's not friendly, but he's kind of a scaredy cat. So having virtual class actually makes him um, visible to everybody, let's say. But he'll probably be joining us in and out as we go through this. So let's talk about these storms and dig down into how hurricanes are developed and what they are and the different stages of different classifications, etc. When we say weather systems, referring to storms, okay, let's just put a general statement out there, and that is that your weather systems are going to be organized phenomena within the atmosphere. We're talking about inputs and outputs, changes of energy and changes in moisture. Okay, so there is constant change all the time when it comes to weather outputs, when it comes to weather systems. And the more inputs exist. So, like for example, let's say the lower the pressure gets in a storm, the more outputs, like rain, a storm or weather system is potentially going to give off. Okay. Um, I'm going to go ahead and switch gears now. Let's walk over to the whiteboard. Let's go ahead and talk about hurricane development. That's going to take really this next block, kind of first half of the page. So at this point, we're going to move over and do that now. Okay, so let's go ahead and talk about hurricanes. Large storms, how they are formed, in particular in North America, what that phenomena is like, and the types of effects it can have. Okay, so we're talking about an area in close to North America. For example, saying this being the United States, here's Florida, the Gulf of Mexico, Mexico itself, okay? So the eastern side of the United States here. This is where the very common occurrences of hurricanes exist. This ITCZ being in our dotted green line here, this would be, actually the ITCZ would be, kind of right below that, as we've learned, and this dotted green line being the Tropic of Cancer. So we're right at that about 22 or 23.5 degree north latitude. So in that area, thing to note is that the weather being so warm there, especially in the tail end of the year. So I don't mean that in, say, December, but after the summertime, as the, let's say, the waters have had a chance to warm up to their hottest point. So summer, say, ends around August, September. Well, there's still a little bit of a warming effect going on between September and October. But basically between late August all the way through October is when you're going to have these type of phenomena, because this water here is going to be so warm. And what happens when we have warm water, or really warm weather in general, we end up with low pressure. Okay, so low pressure systems. And we learned that low pressure systems cause unstable air, and they cause some pretty intense storms to occur, especially things like convection, precipitation, and when a cold front hits a warm front. But those things in particular are what we're discussing. So that low pressure system being built up is key to that. Okay, so just outside just outside this ITCZ. So right in this area here in the Caribbean Sea, okay, where you've got Cuba and the St. Thomas and those type of Caribbean countries, Jamaica, those type of places that are quite nice and places to go for vacations, but as tropical, kind of oasis or places for having a honeymoon or something like that. But these areas are suspect every single year because of this type of phenomena. So what ends up happening is in this region, clouds and low pressure starts to build up right to the north or right around that Tropic of Cancer within that ITCZ zone. Okay, and so that what ends up happening is winds from east to west start to form and start to blow, and we call these winds the easterly winds. Okay, so they originate somewhere down here in the Caribbean Sea and they blow towards, let's call it the Gulf Coast. Okay, the Gulf Coast of the United States and the Gulf of Mexico. So these easterly waves start to form, and that creates a westward movement, okay? And that westward movement is in association with the low pressure system. So again, with low pressure, we've got a lot of heating occurring, okay? So say from the sun, and a lot of heating creating the winds to do what? Lift upwards, okay? And when winds lift upwards around a low pressure system, that's what ends up happening. And so this is occurring out here in the Caribbean Sea. And so what does low pressure end up doing? Well, low pressure spins in a counterclockwise direction. So you end up having winds and it also tries its best to go to the center, to go into that upward momentum, okay? So you end up having examples like this, where you've got arrows moving inwards and moving inwards in this counterclockwise fashion, okay? In like that, okay? Are all around low pressure systems. The lows being in the middle. So these easterly waves are pushing those low pressure systems, okay? And the more they move towards the Gulf Coast, the more that low pressure actually builds up, or the lower that pressure actually gets. Okay, so the lower that pressure gets, the more intense the storm becomes. So pressure, and low pressure in particular, and the lowering, like the literal number, or the millibars going down in number in low pressure creates the most intensity or contributes to the intensity of the storm. So as these patterns strengthen, you end up with these kind of organized cyclonic patterns. Cyclonic being this kind of counterclockwise low pressure or counterclockwise movement because of Coriolis effect, right? And so we have a few different examples, and storms don't just become hurricanes right away. They go through these different stages, and they're classified in these different stages. And so the first one would be called a tropical depression. So tropical depression, I'll just put it here. Depression would be anything less than 39 degrees, or 39 miles per hour. So less than 39 miles per hour, okay? Less than 39. These are all, just put 39. These are all miles per hour here. Miles per hour. Okay, the next thing after that, if the winds continue to increase, then we end up with something called a tropical storm. So I'll just call this storm, okay? It's a tropical storm. And tropical storms range in value from 40 to, let's see, tropical storm, if winds surpass 39, up to 73. So we'll put 39 to 73. I'm going to get rid of this sun here. We already know that exists. Okay, so that becomes a tropical storm.
And these things develop over time, over days. Depending on how far out they originate and how hot and how much low pressure starts, and then how far they have to go. The further they have to move, the more likely they're going to increase into these different stages based on those conditions. Okay. Now, a tropical storm moves on to what's known as a tropical cyclone if the winds surpass 74 miles an hour. So it becomes a cyclone if we have plus 74 miles per hour. Okay, and let's see, cyclone, same name as hurricane. Okay, cyclone or tropical cyclone is the same thing as what we call a hurricane. So I'm going to put here cyclone equals hurricane, just for FYI for our reference in North America. Okay, in the Eastern Hemisphere, so in Asia, these kind of occurrence happens as well. But in Asia, instead of calling them hurricanes, they call them typhoons or just calling them cyclones. Okay, and in the most severe cases, again, I'm talking about surface pressure being low. Imagine that, generally speaking, around sea level, you're going to have surface pressures around 1,000 millibars. And so in the most extreme cases, when this development goes from depression to tropical storm to hurricane level, we end up with pressure ratings or millibars down into the 900s rating, or even lower than that. Okay, so anything with a surface pressure of 900 millibars, let's just put a note here, 900 millibars. Okay, that's the surface pressure, so that's a extremely low pressure, 900 millibars. You're going to end up with surface winds, okay, surface winds of anywhere between 100 over 100 miles an hour up to 200 miles per hour in that case. Okay, and it's still considered a hurricane at that point, because once it goes over 74 miles an hour, the winds, as far as the winds are concerned, everything is classified the same as a hurricane. Okay. The eye of the storm is the most intense part. Or I'm sorry, the eye of the storm, back that up. Forget what I just said. The eye of the storm is in the middle of the hurricane. Okay, the eye of the storm is in the middle of the hurricane. So again, you have winds kind of doing this, and they're moving inwards like this, and there would be one like that. Okay, so right in the middle there, we call that the eye. Okay, this would be called the eye. Okay, and in the eye, the strongest weather is not, let me repeat this, the strongest weather, so like the most intense winds and rains and hails and other things, lightning, thunder, etc., does not exist in the eye, does not exist in the eye. The strongest weather actually exists along the eye, what's known as the eye wall. Okay? Not the middle of the circle, but the surrounding edge of the circle. Okay? So it creates this big tall wall of clouds and weather, and that is where the intensity of the storm is its most heavy or most intense. Inside the circle itself is actually very calm. So inside the eye, inside, let's do it like this. Okay, so inside the eye is calm. The eye wall is where things are intense. Okay, so I'll put calm here. And R inside the eye, that's the eye. Okay, and the eye wall, which is this thing. Okay, so I'll put another note like that. Eye wall is most intense weather. and that's hurricanes.
Great. Okay. So now that we know how hurricanes develop, um, let's talk about some other facts related to them. In particular, um, that the size of a hurricane. Hurricanes can range in size. Okay, so whether they are, and these are miles in size we're talking about. Something that's miles in size, like say for example, 50 miles in size sounds small compared to 1,500 miles in size, but 50 miles would be about the span of the East Bay from say Vallejo to San Jose. That's a pretty far distance for a storm to be, to exist. So anyways, these hurricanes, that would be the small, on a smaller scale. Hurricanes can be anywhere from, like we say, 50 to 2,000 miles in size or more. Um, but like we said in the whiteboard video, it is not the size, the physical size of the hurricane that matters or the storm that matters. It's the central surface pressure, and in particular, how low that central surface pressure is. Okay, surface being close to the ground or close to the water. The lower that pressure is, the closer it is to the ground, the more intense that storm is going to be. It could be a storm that's 50 miles wide and has really, really extremely low central surface pressure, is going to be more intense than one that is, say, 100 times larger than its physical size, but has a relatively normal surface pressure. Okay. So low pressure, you're going to hear me sound like a broken record at this point. Low pressure equals intensity. Low pressure equals intensity. Yeah, and we hit on this a little bit, right? And that hurricanes, they form during the late summer, early fall. Like we said, the August, September, October timeframe. It's almost like clockwork. You can predict, as they call it, hurricane season. And it's because this single phenomena occurs. This would be the one catalyst for that, and that's that tropical sea surfaces. So the water itself, they reach their highest annual temperatures during that late summer, early fall time frame. Okay, so the water reaches its highest water temperatures throughout the whole year. Okay, not in June, not in March, not in December, not in July even. It's rare for it to happen in July. There's a little bit of a lag time, a little bit of a lag where we go from August, September, October for those oceans to really heat up, because water takes longer than dirt or land to get hot, right? It takes a much longer time frame. And that's why we end up with this kind of timeline or time frame every year. Taking a look at the slides, number 14. This is quite an amazing takeaway. So what's happening here is we have, let's see, the example is Hurricane Katrina, which we're going to talk about a lot more in this example here. But Hurricane Katrina, about 15 years ago, 2005, August 31st. So late August, early September, right? Supported by very warm sea surface temperatures. Here's that Caribbean Sea that we discussed, okay? Where the Caribbean, this is the Gulf of Mexico. Here's Florida, Mexico. And look at these surface pressure, or these surface temperatures. These are actual water temperatures now. The darker the red, the hotter the temperature. So 35 degrees Celsius, let's relate that to Fahrenheit. Celsius, you go 35 times 1.8 plus 32. So you're talking ocean temperatures Okay, get this. The water in those very red areas where it's 35 Celsius equates to 95 degrees Fahrenheit. So basically, it's like bathtub water or almost jacuzzi um, um, temperature type of water. Okay, so imagine this huge boiling, almost like a boiling. It's not boiling, but it's like a huge boiling pot of water, and imagine all of the energy that is released from that. Okay, um, so yeah, up to 95 degrees. I'm sure in some areas it gets even hotter than that. Probably gets to 100 degrees Fahrenheit in some areas. Um, and then we also have 33. So here's your frequency of tropical storms and why things are so predictable. This is a 100-year sample, and we have your hurricanes and tropical storms and hurricanes. I mean, the trend is basically the same whether you're looking at the red line or the yellow line. Right around that September mark, in this case September 10th, we can pinpoint as being a time when the most hurricanes and tropical type of storm activity is going to occur. Okay, tropical type of storm activity is going to occur. Yeah, now hurricanes, they are self-sustaining as long as they remain over that warm water. So that means that say they start in the far reaches of the Atlantic Ocean, and as long as they are moving over and continue to move over warm water, especially if the water is getting even warmer, that storm is only going to intensify. It's not going to just go away on its own. Okay, it's going to self-sustain. So essentially, nothing is going to stop it under those conditions. It's just going to get more intense. The thing that does stop it, though, is when the water surface, the actual water temperatures themselves cool down. So that contributes to time of year, okay? Because in the other times of the year, the temperature of the water is nowhere near that 100-degree kind of mark. Sure, it might be 70, 80 degrees, etc. But it's not going to be the same, okay? So time of year, but the other factor, and this is going to be not dependent on time of year at all, is latitude. So right around 25 degrees north and south latitude is where the sea surface temperatures, regardless of what time of year and regardless of if it's September 10th, they aren't quite warm enough to sustain the intense hurricanes as when they started out in kind of that ITCZ zone. So there's a very kind of strict line of where these hurricanes that we talk about in North America occur between that kind of maybe they start out near the equator and up to the Tropic of Cancer, but it's kind of a gradual northwest movement. And once they reach over 25 degrees north latitude, then they kind of phase out. Okay, they kind of phase out, which is why you don't very often see hurricanes hitting, say, somewhere like Boston or New York, etc. Sometimes the storms do make their way up to those regions, but their intensity tails off because the water temperatures are much cooler. So they, it's kind of like the antidote for hurricanes. Okay. Not to say that we don't have an example of something like that. So we're about to get to that. But just some other things to discuss here. We rated we said there were kind of stages of developments of tropical storms, going from our depression, tropical depression, tropical storm to cyclone/hurricane. And then after hurricane, it's just all called a hurricane. Well, there is categories of hurricanes based on miles per hour, so it does continue to get rated. based on something called the Saiph-Simpson hurricane wind scale. So the wind miles per hour is what we use to rate these hurricanes. And this would be a level 1 hurricane, level 2, level 3, level 4, level 5. So you see where we're going with this, kind of these brackets of miles per hour that we're working with here. Level 5, you know, it doesn't get much more intense than that, although it definitely can. And there are numerous examples where it does. But if you're in the midst of a level 5 hurricane, that's bad news. Okay, you're talking 150 miles an hour or more of wind speed. Okay, wind gusts. You know, there's more to it than just wind, say, crashing into, you know, a building or blowing you away or something like that, right? Because maybe you are in a very you know, kind of bunkered down shelter where you know, the winds might shake things around, but they're not going to, say, blow your house over, right? The other thing that the other phenomena that occurs out in the ocean because of these intense wind or high winds is something called storm surge. And so that's when wind drives the water from the sea and it drives it into the land, and it creates very, very tall waves that get taller and taller and faster as they get closer to the shore. So waves that could be upwards of 30 feet or higher, 30 feet or higher. Most even two-story homes aren't even barely 30 feet or higher, okay? Two-story single-family homes. When you see large floods like that, and you see people on the standing on the roofs of their homes, and that's all you really see, the roof of the home. Sure, there's rain that's associated with hurricanes. There's very intense rains, inches upon you know, dozens of inches of rain that falls. But it's the storm surge that really causes the havoc, in addition to the wind, okay? Because the storm surge just is like this huge push of water onto land. And we've got numerous examples of that and how destructive storm surge can be. So here's an example, shoreline of Biloxi, Mississippi. We're going to use Hurricane Katrina as the example. And so I don't get blinded out by this afternoon sun. There we go. So just, you know, take a look at that. Nice kind of beachfront, a pier, a couple, you know, homes, this old looking plantation home. Okay. Now let's look at, what is that? 3 days later. Yep. 3 days later. Why didn't it light up? I guess it didn't light up, but here's a before and after of the hurricane. Okay. Hurricane Katrina. Before, after, not much left. And much of that due to the storm surge that essentially kind of comes onto shore and washes everything away, okay? Crushes everything and then washes it away. This building was probably 200 or more years old. Who knows? Okay, here's some other examples. Something called Fire Island, New York. This very long, thin strip of kind of beachfront near Long Island. Okay, and this is called Hurricane Sandy. This was a more recent destructive storm, 2012. Okay, so take a look at that. And this is late October we're talking about now. So like I said, they can go from August to October. These hurricanes and storms, and after the storm surge, look at that. Okay, look at that. You know, just incredible destruction that can occur from storm surge. And here's those examples. I mean, and they are astonishing to view from the air. Just the amount of destruction that can occur and the amount of water that inundates an area. So let's see. Do I have other slides supporting this? I know I do. Yeah. I don't know why I didn't highlight them here, but oh, I did. Okay, so 43 and 44. Let's take a look from the kind of technical perspective. Here's what's going on. So in the the deeper part of the ocean, the wave doesn't really seem that intense, doesn't really seem that tall, okay? But still, you're talking pretty, large waves that you would experience. Now, those waves, as they move closer to the shore, they're going to get even taller and move faster because the ocean floor itself, as you get closer to the land, that water does this, and it kind of pushes up against it like that, and it pushes up, and it intensifies its speed because it's still the same amount of force and the same amount of pressure moving it towards land. And so it gets even taller once it hits landfall, which is, where possible beachfront homes or other things exist. And you have examples like something like this. Okay, this is storm surge after this was called Hurricane Rita, which was after Hurricane Katrina, actually, but all around the same kind of time frame. Just take a look at this. You have very low elevation kind of marshlands here. These are, 10, 15 feet maximum type of elevation. In the Bay Area, I think we actually have some pretty similar types of shorelines, right, and landscapes, don't you think? However, I don't think it's very possible for something like this to happen here. Well, reason being is because we don't have the ingredients which would make this kind of hurricane happen, and those being, one, the easterly waves blowing into us because we're on the west coast, and most importantly, number two, the water here is very cold. Okay, it is far too cold on the San Francisco Bay for it to support any type of large hurricane activity. Maybe off the coast a little bit, or in the ocean, kind of near Southern California and Mexico, those places, but it would be an extremely, you can never say never, because I'm going to show you an example here in a minute, but it would be an extremely rare occurrence for something like that to end up hitting us here in the Bay Area. This is all from storm surge that we're looking at here, all from storm surge. That wall of water just crashing, boom, crashing into the land, and then just a lot of it stays there and it doesn't subside for days and days and weeks. Eventually it does either evaporate or get pumped out or kind of falls back into the sea or goes into rivers or other waterways, or it kind of forms new channels. But yeah, it's a pretty intense thing. So here we are. Okay, the worst hurricane ever, as far as damage is concerned, is in U.S. history is Hurricane Katrina. Hurricane Katrina was a 920 millibar. Okay, so 920 MB central surface pressure, and it hit urban New Orleans in 2005. Now, I'm not saying that it was the lowest pressure ever, or that it was the most intense winds ever, or the highest mile per hour winds ever, but we're saying damage-wise, kind of all of the, let's say, the perfect storm, right? Where you have this Category 5, I was calling them levels earlier, these would actually be called categories. So Category 5 hurricane, and hitting an area that is very urban and very dense, in New Orleans, Louisiana. Okay, something that is quite rare to find from a natural disaster. This amount of death in the United States, because we have such a robust and built-up infrastructure here that can support destruction like that. Okay, but nevertheless, over 1,000 deaths and over $100 billion in property damage. Okay. Now this is 15 years ago. It'd probably be double or triple that by now, by nowadays standards, right? Watch this video. You gotta watch this video. I want everybody to watch this because it will be an eye-opening experience for you. Absolutely watch this YouTube video, okay? I'm gonna go ahead and pause and let you watch, and then we'll come back. Okay, so intense, right? Let's talk about the second worst. The second worst damage-wise. U.S. history was known as Hurricane Sandy. We looked at a couple pictures of that a moment ago. Hurricane Sandy hit the metropolitan area of New York City in 2012, okay, known as the October disaster. You know, Hurricane Sandy was not the most intense storm, and it didn't have the most heaviest winds ever, or the heaviest rains, or the largest storm surge ever. But the fact that it hit the most dense and most populated area in really, you could make the argument in North America. I mean, next to Mexico City, that would be the only closest rival, but that's inside of a 5,000, 6,000 plus elevation, so hurricanes are never ever going to hit that. For a hurricane to hit New York City caused incredible damage, incredible amounts of damage. Okay, in particular to the infrastructure and to the roadways, subways, that kind of thing. So I want to take a look at these. I think these are photos, actually. Let's do that now. Okay, here is, and it's not just New York City, it's New York City's metropolitan area, right? Oh gosh, I don't want this stuff. Get out of here. Turn off your ad blocker. Sure. Sorry, this is pretty annoying. I didn't realize it was going to do this right in the middle of my lecture. How do I turn this off? Disable. Okay. Sure, let's try this again. With lots of ads. Okay, here we go. Simply put, it's underwater. So here is the results of Hurricane Sandy over New Jersey. This is supposed to be Sandy Beach front here, folks. Okay, all of this stuff underwater. It's not just things becoming underwater. You have infrastructure like electricity, utility, power poles, those kind of things. Fires are going to start, right? Leaks of gas lines, etc. Those things could occur. This one was always one that stuck in my mind ever since the day it happened, is the amusement park that they had along the beachfront. And I remember watching and looking at pictures of the roller coaster route in the middle of the ocean. It was just crazy stuff to imagine. Yeah, all results of storm surge in this beachfront community. And this took years and years and years to build back. Not something that a community can just recover from right away. Okay. So why, as we just discussed, why or how is a better way to say this? How did Sandy even become what it did? Well, Hurricane Sandy was a combination of really a number of things all at once. It was a storm from a hurricane from the Gulf or from the Caribbean that had been built up. And then there was, at the exact same time, another storm, not quite hurricane level, but a huge storm in the North Atlantic, in the Atlantic Ocean at the same exact time. And those two storms converged together. And so once they converged together, they essentially converged right at the point where they were going to make landfall with New York City's metropolitan area. And so this was I guess you could say once in a lifetime type of events, because it's such a rare thing for it to happen. But because the other northern storm was in existence and the other northern storm contributed to, or let's say added to the intensity of the original hurricane, that's how this storm was ended up, how this hurricane really it was at that point a tropical storm, because it wasn't quite a hurricane at that point when it made landfall. But that tropical storm had such an impact damage-wise that it did to New York metropolitan area. Okay. Yeah, a couple other things to note here. You know, storms, it just depends on the area of the world we're talking about. You know, it's one thing to discuss the United States and say thousands of deaths and how much of a tragedy that is, and it really is, right? We can't downplay something like that. But storms of similar intensity, they can occur in other parts of the world as well. So Asia is and Eastern Asia and South Asia, where India, Southeast Asia, those kind of places are also very much hotspots for hurricanes, so typhoons. And a lot of those areas are not developed like we are here in the United States. So they do not have the infrastructure to support the people when something like this occurs. And we see tens of thousands of lives lost in those types of events. For example, 1970, the tropical cyclone killed 300,000 people in Bangladesh because they had nowhere to go and they did not have any infrastructure to build up to protect themselves from this type of intensity of a storm. Okay, and this is a pretty common occurrence that we see in many other parts of the world every year. Okay, many parts of the world every year. Okay. Yeah, so mid-latitudes, we talked about frontal precipitation, and in mid-latitudes, the most intense weather. So now we're talking about places like, you know, like we can say mid-latitude, which the Bay Area is a mid-latitude, but let's, you know, we're in a maritime climate, so we're kind of in a different position than say somewhere like Denver or Nebraska or you know, Chicago would be, for example. Those would be the mid-latitudes we're thinking of. And your mid-latitudes, your intense weather in your mid-latitudes is mostly a result from air masses colliding with different temperatures. So that's all, sorry, that's not frontal. No, it is frontal. That would be frontal precipitation. So frontal air mass, frontal type of precipitation process, air masses colliding. So cold versus warm, and they're crashing into each other. Those are what's caused the most intense types of weather and strongest storms in those latitudes. Okay. Okay, so let's see. Movement to most latitudes. Yeah, and we discussed this a little bit. We had the example of your jet streams, something called the polar jet stream, and it separates the polar front from everything else. That really controls the formation or the movement of the where the mid-latitude weather systems go. So if that polar front diverges down, you know, below Canada, then we're going to fill that kind of colder air, and that colder storms are going to come through, and these storms themselves in mid-latitudes will be more intense because you have cold air coming from the north and warm air coming from the south, and the more they crash into each other, like for example from this polar jet stream causing that type of occurrence. So it's all about the position of the polar front, okay, the position of the polar front and the strength of the polar and subtropical jet streams. So we have polar front going this way, we have subtropical jet streams going this way, and the position that they're in related to each other, and the strength of each one of them is going to be important for what happens to air masses, and it's going to influence source regions in mid-latitudes. So, you know, all of this kind of last section here we're talking about is that the weather in the mid-latitudes is much more variable over time in the same year. And, you know, cold weather meeting warm weather is going to contribute to intense weather. Let's put it that way, okay? Let's see. let's see. Yeah, so let's go ahead and close. I'm going to go ahead and stop now. That's really the end of this this section or this chapter, this unit, all about hurricanes. I hope you enjoyed it. It's always one of my favorite ones to explain and talk about.